All right, hello class. We're going to be working on Unit 1, Lesson 1 and 2, which is types of functions. Go ahead and write down your title, grab your colors, everything you need for today's lesson. All right, so these are our learning targets today. We want to be able to talk about some key features, the types of graphs, etc. These are our learning targets for today. All right, so here are our different types of functions. So we're going to start off with linear. Linear is going to be a line. You should be very familiar with that. Its parent function is y equals x, and it looks exactly like a line. Next function is called a quadratic. Okay, we should be familiar with that from Algebra 1. It is the U-shaped graph. You may have also heard the word parabola. Okay, parabola. Okay, so its parent function is y equals x squared. And again, it's shaped like a U. I usually use the terms smiley face and frowny face to describe a quadratic function. Our next function is called the cubic function. The cubic function is the y equals x to the third power. It looks like a little snake going up the tree, I like to call it. And its function is, again, a cubic. Think of a cube, 3D. That's going to help you remember that 3 is in the exponent. Our next graph, or function I should say, is an exponential graph. We have exponential growth and we have exponential decay. Okay, and so what that is it's like an L. Think of L for exponential. So when we're talking about growth, we obviously are talking about increasing. So its base, that 2 right there, is the B, and that B lets us know whether or not it is a growth or a decay. So if it's a whole number, it's a growth, and if it's a fraction, it's a decay, okay? And so think L for exponential when you're looking for those graphs, and when we get closer to exponential functions, we'll detail more about what they actually look like. Let's talk about absolute value, okay? V for value is the shape of the graph, and it looks like the parent function is those jail bars, I like to call them. It's y equals the absolute value of x. No transformations have occurred. Again, it's v for value. If we talk about square root function, we should be very familiar with what a square root looks like. We've been doing that for a little bit. And its parent function is y equals the square root of x. That's like a rainbow, I like to call it, because it's going to start from the origin, which is 0, 0. And it's going to shoot out like a rainbow, okay? Almost as if the rainbow does not come down though. And then lastly is a cube root, which is the inverse of a cubic, okay? It's the inverse function of that. And think of roots. So the 3 there is the cube root, and it's like the snake not going up the tree, but now slithering on the ground, okay? Because think about the roots of a tree. So those are our different function types. All right, so let's talk about one more function type, is rational functions. And so a rational function is a function that has some restrictions. So let's talk about that. So its parent function is f of x equals 1 over x. Okay, and its graph actually has 2 different types of shapes. As you can see, one is split, one is not. And with that being said, we have to talk about its restrictions. So it is symmetry across the y equals x line, okay? And so we have one graph that's in the first quadrant and one graph that's in the third quadrant. And it has specific restrictions. Again, its domain is that it cannot be zero, like it cannot touch the x-axis at all. And same thing for its range, it cannot touch the y-axis at all. So it actually has two restrictions, so it will never have any intercepts, x or y, okay, because it cannot touch the x-axis nor the y-axis, okay? And here's why. So think about it. A rational function is like a fraction, and so when you divide, you can't have 0 on the bottom because you're going to get an error if you put it in a calculator, right? So that is why x can't be 0, because I can't divide by 0. So that the x's values are the domain, and the range is the y values, okay? So that is our rational function. Okay, so let's talk about linear functions a little bit more in depth. So we have our 4 different types of slope. One positive uphill, negative slope downhill, horizontal slope is equal to 0, and vertical slope is undefined. It's like you fell off the cliff. And so linear functions have a domain of all real numbers as well as a range of all real numbers, because it goes on and on forever in either direction, and it has x and y intercepts. Okay, so go ahead and copy this information down. Okay, let's talk about the different forms of a linear equation. And so we have standard form, which is ax plus by equals c. We have slope-intercept form, which you should be the most familiar with, y equals mx plus b. And then we have point-slope form, which is y minus y1 equals m times x minus x1. Okay, so these are the 3 different types of forms. Go ahead and write these down. Remember, m stands for slope, b stands for the y-intercept in the slope-intercept form. And then the point-slope form, remember that you're actually using a points, okay, a points. Remember, linear, its exponent is 1, so that should let you know if you see 1x that we're talking about a linear equation. Okay, so these are the different types of forms that you need to know and be able to recognize for linear equations. Okay, again, so go ahead and write these down. All right, so a linear table. So let's talk about different tables. How we know it is a linear table is that we're getting the same rate of change. That's another word for slope, okay? So the change in y is the same as well as the change in x. It's a constant change, okay? And so as you can see, it is constantly changing by 2 each time for the y values, constantly changing by 1 for the x values. So that lets me know this is a linear table, okay? Because the change is constant, okay? So that's how you know it's a linear table. Let's go to quadratic functions. So the graph of quadratic function, again, like I said earlier, is called a parabola, okay? And in standard form, you're going to use ax squared plus bx plus c. You should be familiar from factoring using that. And so we have a frowny. Okay, so again, the vertex is notated by hk. And so with the domain, it's all real numbers, and the range depends on the vertex, okay, which is your k in the vertex, and it has x and y intercepts, okay, x and y intercepts for the quadratic function. So go ahead and write that down. And here are the 3 different forms of a quadratic equation. There is vertex form, factor form, otherwise known as intercept form, and standard form. Okay, so you should be familiar with factor form and standard form. Again, vertex form is just showing you the HK, okay? So with that being said, I want you to go ahead and copy down each form. We will practice later on how to move between the different forms. So go ahead and write this down. Okay, Hopefully you have a chance to write this information down. Again, these are the three forms of the quadratic equation specifically that we need to know. All right, moving on to quadratic tables. So this one's a little bit different, unlike the linear tables. The constant change would happen the second time, okay? The second time. And what also would help me know is that I'm looking for perfect squares, right? Because the quadratic function is y equals x squared. So I'm looking for some perfect squares. 1, 4, 9, 16, 25, and 36 are perfect squares. But again, another way to look at it is if the second time I check for the change, that second change is constant, then it is a quadratic function. That's how I'm able to know from a table. So notice how the second change was 2. Okay, moving on to exponential functions. All right, so remember I told you earlier when we're looking at the L for exponential that there are different shapes of the exponential graph. And so depending on your A and your B in your original equation, you will have a growth or a decay in either direction. Remember that its domain is going to now be all real numbers, and your range depends on your asymptote, okay? The asymptote is what it cannot touch. As you can see, it is diverging in different directions. There is never going to be an x-intercept for an exponential function, but the y-intercept is okay, and it is the A in your original equation, okay? So think of the asymptote as the cannot touch line. And we will specifically do more examples later on so that way you can tell the difference between a growth and a decay. So go ahead and copy this information down. All right, a table, again, exponential tables. Remember we have growth and we have decay. If we're looking for a growth in a table, we should be changing really, really fast by using multiplication. Okay, so notice how we're multiplying by 3. It is usually the B, okay, when the B is greater than 1. And then the decay is when we are dividing, okay? We are dividing, or you see some type of fractions, decimals, anything like that, because the B is usually a fraction in the original equation. So if you notice, again, like I said, fractions, decimals, really, really big numbers that go like really, really fast change, then that should let you know that is exponential. It can even be really, really small numbers. Again, fractions are really, really small numbers. That should let me know it's an exponential type of function from the table. Okay, so go ahead and write down this information so that way you can take a look at growth versus decay. Excuse me, sorry. Okay, so again, write down this information. All right, let's talk about absolute value functions. It's very similar to the quadratic function with it has a vertex and it shifts and its transformations are the same. The only difference is V for value for absolute value and U for quadratic functions, but they have the same domain, which is all real numbers, and the range still depends on the vertex, which is the K in the vertex. And it also has intercepts, both X and Y. So it again is very similar to the quadratic function. I went ahead and showed you some different examples. Now let's look at the tables. Okay, again, remember V for value for the shape of the absolute value graph. And notice how all the Y values are all positive values. Absolute value is distance from 0. So think about distance is always positive, whether or not you take steps backwards or forwards, you still took steps. So distance is always positive, so therefore your Y values should all be positive. That should be a good indicator that it's an absolute value table. Not always, but more likely than none. You would be able to tell it's a table because notice how all of these values were positive. But if you look at the second example, they don't all have positive values, okay? And so with that being said, what you would have to do sometimes with your table is to actually graph it and see whether or not it's giving you a V shape or a U shape, okay? So sometimes finding absolute value tables are kind of harder than the other functions. But remember for quadratic, we're looking for the second change, okay? So it's not going to always be positive values, but it's going to be close to that. most of the time. Okay, so now let's do a problem together before you try one on your own. So we're going to actually do this one first. Sorry about that, guys. Okay, so we're going to actually do the graph first. So we're looking to figure out what the shape is. It looks like an L, upside down L shape. Remember L for exponential, so I'm looking for the parent function of that. In order to figure that out, I need the x and the exponent for exponential. And so I'm trying to figure out whether or not it's going to be a growth or a decay. Okay, and it's not touching the x-axis, so it's another indicator that it is an exponential function. Okay, and if we take a look back at our examples that we wrote down earlier, it's going to help us figure out if it's a growth or a decay, but for sure we know it's exponential, so we want an x in the exponent. So again, let's take a look back at the different examples so that we can figure out whether or not it is growth or decay. Okay, notice again that it's x and the exponent for exponential. So we know that it's exponential, so we should be looking for now the difference between the growth and the decay. Okay, so let's take a look back at this. So the type of shape we're looking at, it looks like the green one, right? It looks like that one. So that one is actually going to be a decay because the b is in between 0 and 1, meaning it had to be a fraction. Okay, so it's actually going to be a decay. So we're going to pick the one with the fraction, 1/2 to the x power. Okay, because 1/2 is like 0.5, which is in between 0 and 1. Okay. All right, so now let's look at our table. So let's look at our values. Our values in the y is changing by 1. That's a constant change, right? Same thing with my x values. It's changing by 1. So if it's a constant change, remember we talked about that. That is a linear function. Okay, that's a linear function. So we're looking for 1 and the exponent, which matches the first one, y equals x. Okay, y equals x. Okay, let's do one more one more we do before you do a try. All right, so this we do we're doing again is y equals the absolute value of x plus 5. Okay, this should be easy because those gel bars are there. Know that they're absolute value bars, and so its original function is an absolute value function. So we're looking for the same parent function with those bars, and that's going to be y equals the absolute value of x. Okay, so that was actually easy to figure out. Now for this, go ahead and pause the video and try and see whether or not you can figure out from the table what kind of function it is. Okay, so hopefully you pause the video and you try. And so let's talk about it. So we saw fractions, so a whole number. So automatically that should have made me think it was exponential. And because it's going up, those numbers are going up from fractions to a big number, it should be a growth, not a decay. So I should be picking y equals 2 to the x. Okay, remember x and exponent for exponential. And again, the whole number was growth and the fraction is decay. Okay, just like the one that we did before. So hopefully you got that. Now pause the video again and try these two, the graph and the table. Okay, so hopefully you tried it. So remember that in the graph, the snake is going up the tree. It's going in opposite directions. So it is going up the tree, so we should be selecting the y equals x cubed and not the cube root, right? Because remember the roots of the tree are at the bottom, they're on the ground, but the snake is actually climbing up the tree. So its parent function is going to be y equals x cubed. Now let's talk about the table. So with the table, it is changing by -3. It's going down by -3 on the first half, and then the other half is going up by 3. That lets me know it's absolute value because that means there should be an axis of symmetry, okay, on either side of the graph. Okay, and so because that the change is going to be matching either side of the graph, it is going to be absolute value function, okay, because the absolute value function is more like a piecewise function, as in two parts. One part will be going down, one part will be going up. That's why it creates a V for value. Okay, so that matches an absolute value table. Okay, let's talk about different types of notations. And so let's first talk about inequality notations. We should know the alligator from elementary, maybe even middle school, greater than, less than, greater than or equal to, and less than or equal to. We use this to talk about domain and range of different types of functions. So we want to be familiar of these different types of notations. So go ahead and write these down. And the examples I put on the side as well, so that you can see how some things are going to be written for domain and range. Okay, so this type of notation is called the set builder notation, and it says the set of all x values such that x is less than or equal to 2 is an example. So that's how you read that out loud. Go ahead and pause the video and start writing that down. Okay, so then we also have interval notation. So that would be parentheses and brackets. So the parentheses are for not included in the answer, and the brackets are for included. The parentheses are an open circle, and the brackets are a closed circle when they're on the number line. So here are a couple of examples just to show you what that looks like. You never put a bracket for infinity because infinity is not an actual number. You always use parentheses. So go ahead and write that stuff down. So now that we can try the different examples. So we're going to do the first one together. It is already given to me in inequality notation, and they want it in set builder notation as well as interval notation. So if we start off with the set builder notation, that's the squiggly lines. Remember, we read it as all values of x such that blah, blah, blah. So we're going to write the squigglies first. We're going to write the x and then that slash. Okay, remember that slash means such that. And then we're going to write it exactly how it was in inequality notation, which would be negative infinity is less than x is less than or equal to 9. So it's very easy. It's just a more fancier way to write it already from inequality notation. Now for interval notation, remember we're going to always use a parentheses for an infinity symbol because it's not an actual number. And we're going to use a bracket for the 9 because we have less than or equal to, okay, it means it could be 9 and smaller. So 9 can be included in your answer. So we're actually going to use a bracket for the 9, okay, parentheses for the infinity and a bracket for the 9, okay, because infinity is not an actual number. Okay, go ahead and try these other options and pause the video. Try these other two options and pause the video. Okay, so hopefully you pause the video. So let's talk about the blue one first. So inequality notation, remember it's literally taking the same thing from the set builder notation already, which says -5 is less than x is less than infinity, okay? And when we talk about interval notation, notice how we didn't have any lines underneath, right? It's just less than. It's not less than or equal to, it's just less than. So we're going to use a parentheses for both the -5 and the infinity symbol. Now, if we look at the green one, again, they gave it to us in interval notation. So it lets me know that there's going to be a included answer for 3 and a not included answer for 12. So that means I'm going to be using either less than or equal to or greater than or equal to. In this case, because it goes from 3 to 12, I'm going to use the less than symbols because the x should always be in the middle. And I'm only going to use a line for the 3, but not for the 12, okay? Because these guys have to be going in the same direction, all right? So again, hopefully you were able to get that. If not, we're going to do some more practice in class. And so go ahead and finish writing this down, and you guys have a good rest of your day.